At this point, there's one thing I need to explain to you. Remember earlier, I told you that we'll use those I sub phi to approximate I naught. So now I have to tell you how this works. How I sub phi approximate I naught. I sub phi approximate I naught in the following sense. For any open neighborhood U of identity and any Fj in Cc plus of G, where J is from 1 through n, and any epsilon greater than 0, there exists phi in Cc plus of G with supportive phi contained in U such that I naught of Fj minus I of phi of Fj has absolute value less than epsilon for any j from 1 to n. And now let us verify this. Check. By construction, we know I naught is taken from the intersection of k of b's, where b ranges from all open neighborhoods of E. By definition, each k of b is a closure of such sets. I sub phi, the support of phi, is contained in V. Because we are living in essentially an infinite product space, we need to consider, for this purpose, a neighborhood of I naught in the infinite product space. So consider the following neighborhood of I naught in X. This is the infinite product of X of F's, where F ranges in Cc plus. So we consider such sets. The infinite product of Y sub F's, where F ranges in Cc plus of G, where each Y sub F is defined as follows. There are two cases. First, will be the interval from I naught F minus epsilon to I naught F plus epsilon if F is equal to Fj, where this Fj is same as Fj here. There are n many of them. So here J is from 1 through n. And the second case, Y sub F will be equal to the whole space Xf. if f is not in the set of functions from f1 to fn. This infinite product of yf is really open by the definition of product topology on this infinite product space. And clearly, the set contains I0. This should be easy for you to see. But don't forget, I0 lives in the intersection of all those KVs. What this tells us is that this infinite product of y sub f's has non-empty intersection with the intersection of all those KVs. But what is each KV? KV by definition is the closure of such sets. I sub phi where support of phi is contained in V. So KV is the closure of this set. Therefore, we have the following intersection, non-empty. For any B, which is the open neighborhood of E. This is by the definition of the closure of a set. If an open subset has non-empty intersection with the closure of the set, then it must also have a non-empty intersection with the set itself. Or I should rather say this is maybe the most basic property for the closure of the subset in general topology. So there exists phi in CC plus of G with the support of phi contained in V such that I sub phi is in infinite product of y sub f's. And if you go back to the definition of those y sub f's, in here, we got precisely what we wanted to prove at the beginning. We got precisely this guy. And this verifies this approximation property of I sub phi towards I0. The only difference is that we replace U with V, just a replacement of a notation, but that doesn't matter. And we can also explain this in another way. If you are familiar with the relation between the product topology and the pointwise convergence topology. Since the product topology coincides with the pointwise convergence topology, for any f in CC plus of G, there exists a sequence of phi sub n's such that I sub phi n of f converges to I naught of f. Here, we can use sequence rather than nets because this infinite product space is Hausdorff as the infinite product of Hausdorff spaces. So we can use sequence to describe this. If you don't understand the meaning of the product topology coinciding with the point set convergence topology, it doesn't matter. Just ignore this part. I just want to give the explanation to this from another point of view. However, even if you don't know this fact for product topologies, you should still be able to see this part directly from our argument above or from the thing in this green box directly. Because here we're just taking one function in CC plus of G. But in the argument above, we are taking n many f's. Those n many fj's are arbitrarily chosen. So this is really a special case.